This video demonstrates the workflow for a fracture parameter evaluation of an arbitrary crack in an X joint. A surface body, created in a geometry modeling application, is used to represent the arbitrary crack. The crack can be planar or non-planar. For this video, we have used a circular shape to represent the arbitrary crack. The exterior edges of the surface body define the crack front, and the surface itself defines the discontinuous crack plane. These geometric inputs, along with additional input parameters on the arbitrary crack, define the region and shape of the generated crack mesh. We have imported the X-joint model into Mechanical. Let's zoom in on the surface body. The first step is to specify a tetrahedron mesh method. We only support the tetrahedron mesh method for the base mesh in a fracture analysis. Now we'll create and specify the arbitrary crack using a specific plane for the coordinate system. The X-joint is the geometry selection. The coordinate system is specified as plane 15. The crack surface property is scoped to the surface body, and the largest contour radius property is specified. At this point, you can view graphical representations of the buffer zone, as shown by the box enclosing the surface body, and the number of mesh contours as shown by the bullseye graphic. You can scale the mesh contours and the buffer zone using the associated properties. When you are setting up the arbitrary crack surface selection by picking the surface body, it automatically becomes a construction body. We can then generate the crack mesh. Internally, the crack mesh generation is performed after the creation of the base mesh. By default, the crack mesh generation automatically detects the interface boundary and creates a node-based named selection for the crack front. Selecting the automatically generated named selection for the arbitrary crack displays the intersection points. Turning on wireframe mode, you can see the crack front nodes. For this analysis, frictionless supports are specified on the ends of the tube, and a direct pressure is applied in the upward direction. Let's solve the analysis. Following solution, a fracture tool is inserted and results are specified. We can see that the stress intensity factor K1 is path independent except for the first contour. Typically, the results of the first contour are neglected due to the proximity of the contour to the crack tip. Similarly, we can see that the J integral is also path independent. In general, we can review the results of the other fracture parameters like T-stress and material forces as well. That concludes this demonstration of the workflow for a fracture parameter evaluation of an arbitrary crack in an X joint.